Hello everyone, and welcome to our latest Code Presents webinar, Improving String Handling Performance in C#. We're excited to have Code Magazine author Joydip presenting for us today, and we're looking forward to learning how to improve string handling performance. My name is Jim Duffy, and I'm responsible for the marketing and sales efforts for all of our code services, including Code Magazine. But of course, Code is so much more than a magazine. Code's continuing mission is to help people build better software. We're a Microsoft partner and provide a number of services under the Code brand umbrella, including building custom software solutions on-prem and in the cloud, modernizing legacy applications like Visual Basic 6, Fox Pro, Access, educating developers with webinars and training courses, providing developer resources to augment your development teams, as well as supporting and maintaining existing applications. Our team of expert developers and consultants are ready to help you with your project. Your ticket to free consulting is our very popular free hour of code service. It's a free hour on us. No strings, no commitment, no credit card required, just free help from our code experts. It provides an opportunity for you and your team to meet with our experts to discuss anything you could use our help with. Slots are limited, so reach out to me today about getting a free hour of code scheduled for you and your team. We are hiring developers. Come join the Code Consulting team. Follow the link for more details. If you like what you see here today, or have seen in our prior webinars, please subscribe to our YouTube channel, follow us on Twitter, like us on Facebook, and connect with us on LinkedIn. Code Magazine is the leading software development magazine written by expert developers for developers. All registered attendees who don't already subscribe will automatically receive a free digital Code Magazine subscription. Upgrade your subscription to a print subscription, and you'll receive our latest .NET 7 Code Focus issue for free while supplies last. I've also included a free subscription link here for you to freely share with others who couldn't make it to the webinar today. The Code mobile app is available for both iOS and Android. It's the ideal way to read Code Magazine on the go. How would your C# code stand up to a security review? Hopefully, you'd be okay, but hopefully really isn't good enough, is it? Learn to develop robust and secure C# applications in our online 3-day hands-on Secure Coding for C# Developers course. Register today for courses starting in 2023. Have you heard about Photino? Photino is an open source project that the Code team is involved with that allows .NET developers to create native cross-platform desktop applications using web development technology. You can leverage your HTML, CSS, and JavaScript skills to create desktop applications that run on Windows, Linux, and the Mac. It's like Electron, only smaller and much more lightweight. Learn more at tryphotino.io. We would like your feedback about this webinar in the form of a quick survey. The survey will be available once the webinar has been underway for a bit. We want your feedback, and we're willing to pay $100 in the form of an Amazon e-card to one lucky attendee. A name will be drawn from the entire webinar's registered attendee list, and a completed survey is required to qualify for the e-card. The survey link is on this slide, and we'll post the survey link in the chat window as well. The slides and recording of today's webinar, and all of our webinars, will be available on the Code Presents webpage on the Code website. All registered attendees will receive an email after the event directing you to the slides and the webinar recording as well. Our presenter today is Joydip. Joydip is a Microsoft MVP, is a popular Code Magazine author, is an author and speaker, and has over 25 years experience in software development. If this is your first time attending one of our webinars, welcome and thank you so much for joining us. If you've attended one of our webinars in the past, welcome back. Okay, enough from me. Thanks for listening. Take it away, Joydip.
Hello and welcome to this screencast on improving string performance in .NET. I am Joydip. I was a Microsoft MVP in ASP.NET from 2007 to 2012 for 6 consecutive years. I'm an author and a speaker. I have authored 9 books and I have reviewed more than a dozen books. I have also written almost 1,000 articles on .NET and its related technologies in some of the leading websites in the world like CodeMag, MSDN, InfoWorld, etc. In this screencast, we will take a look at the strategies that should be adopted for improving string performance in C#. But before that, we have to understand how the CLR works. We need to understand how strings are represented in the memory. And of course, we need to benchmark string performance, and that's what the agenda is all about. We will conclude by taking a look at the best practices that can be followed for improving string performance in C#. In this session, we will be using Visual Studio 2022 preview and C# 10. So Visual Studio 2022 will be the IDE, the integrated development environment, where we will be writing our programs, and the C# 10 will be the language, the programming language that we will be using. The CLR provides several services such as the common type system, the common intermediate language, memory management and garbage collection, just-in-time compilation, thread management, exception handling, security. The common type system is a standard that specifies how .NET types are actually stored in the managed memory. The CTS permits the coexistence of several languages targeted at the CLR. The CTS is adept at defining how types in the managed execution environment of the CLR are declared, used, and managed. So what this means is that in order to ensure that the languages targeted at the CLR, they can understand each other with respect to the types. I mean to say, you define a type, an integer type in C#, and then you try to use that. So, and then you compile that, your code, and create a library, and then you import it in a VB.NET project. You will be able to use it, but provided you use the CTS type. Like in case of integer, you have to use int32 or int64, like that. So there are certain protocols that you have to follow, but the bottom line is that the common type system ensures that there is a type portability across all languages that are targeted at the CLR. The CTS provides support for the following 5 categories of types, and these are classes, structures, enumerations, interfaces, and delegates. The common intermediate language is another component of the CLR, which is a platform independent language that is used to write source code for .NET applications. It is a collection of platform independent instructions that is created by the compiler from the source code. So we were talking about IL. So the common intermediate language is that IL. So when you write your code in C# or when you write your code in F# or VB.NET, when you compile it, the output is IL code. So that is common intermediate language. The common intermediate language is a set of semantics used by the CLR language. The common intermediate language is a platform independent language in the sense that when you compile your code written in C# or F# or VB.NET, the IL that will be generated will always be the same. So I mean to say, if you are using CLR on your Windows machine and you are compiling your code written in C#, the instructions that would be generated for the same program when compiled on CLR that has been hosted on a Linux environment will be the same. And of course, the just-in-time compiler converts these CIL instructions into machine code at runtime. In other words, the GIT compiler turns your CIL code into machine-specific code for the target environment. That is the environment in which your application must run. Now we come to the most important aspect in our discussion. We will be discussing this time and again, and that is memory management and garbage collection, because our session is on the best practices that should be followed to improve the performance when working with strings in .NET. So we need to understand what is memory management, how memory management is taken care of by the CLR, and what is garbage collection and how does it work. Because if we don't understand these basic things, it would be difficult for us to know what are the pitfalls of writing a particular block of code which might land you into trouble. So memory management in CLR, when we say it is, so there are 2 areas in the memory. One is a managed heap and one is a stack. And of course, you also have the unmanaged heap. So that is not managed by the CLR. In the unmanaged heap, you have I mean, you can write code which accesses the memory, like pointers, and it is not in the control of CLR. So suppose you are trying to write a program that will access the COM component utility in C++, so that you might be, I mean, you might have to invoke that in an unmanaged memory component, because that is where it will be loaded. In the context of the CLR, you are in the managed heap, you are not allowed to write pointers. You are not allowed to access memory addresses. So in the CLR, in the context of the CLR, basically there are two types. One is the reference type and one is the value type. Value types are your primitive types like int, char, float, double, etc. And your reference types are the objects of your classes, the classes that you are creating in your applications. So the reference types are all created in the managed heap, and the CLR allocates address space from the heap automatically as long as there is enough memory available to allocate. Now we come to, so this is how memory management takes place. So in the managed heap, it grows as the requirement for more memory comes, the request for more memory comes to the CLR. The CLR would allocate more memory for that particular object depending on the availability, of course, the availability of the memory. Garbage collection is one of the most important aspects of CLR. So what it says is that, like in .NET, in .NET environment, in .NET or .NET Core, you don't have to, you create objects, but you don't have to think of or rather bother about releasing the memory allocated by those objects. The garbage collector is a component of the CLR which takes care of freeing up the memory. So the common language runtime creates an object by taking memory from the managed heap. As long as the address space in the memory space managed heap is available, the runtime will keep providing new object space. Now let us understand on what circumstances the garbage collector would be called. That is the conditions for garbage collection. A garbage collection cycle will be triggered when any of the following is true. One, the system is low in memory, in physical memory. The available physical memory is insufficient for the executing application. And that would be detected by the operating system, and the operating system will send a notification accordingly. The other reason which might trigger a garbage collection cycle is that on the managed heap, the allocated objects have taken up much more memory space than that is permitted or acceptable. This threshold is updated as, this threshold in the sense, this acceptable value, the value of the memory that an application can allow its objects to consume. So that is actually continuously updated as soon as or as the process is running. The other reason which might trigger a garbage collection is a call to gc.collect. So this is an explicit call to the garbage collector. So the first two reasons are implicit. You don't have to write any code for that. It would be triggered automatically. Of course, you have written some code due to which there are a lot of objects that have been created, and it has crossed the threshold. So that's different. But you are not writing any specific line of code that will trigger the collection cycle. But in the third case, you are making a call to gc.collect, which is an explicit call to the garbage collector. So you actually don't need to invoke this unless there is any specific reason to do that. We will discuss this. And this is because the garbage collector runs continuously in the background thread. You don't have to think of calling the gc.collect method at all. And that in most circumstances. But let us understand when the gc.collect method might need to be called by the programmer. But before that, let us understand generations. The managed heap is split into logical, you can say, boundaries or logical chunks of memory, which are, so these are not physical divisions, these are just logical partitions. So these are known as generations. So the CLR splits the available managed heap into three generations, 0, 1, and 2. The short-lived objects, I mean the objects that have a lesser duration or lesser longevity in memory, so it will be there in the memory for a shorter period of time. So those objects are usually created in generation 0. And then in generation 1, those objects are promoted to generation 1 if they sustain a garbage collection cycle. So I mean to say, the garbage collector has been called by the background thread implicitly, and the runtime would figure out that the objects, some of the objects in generation 0 cannot be cleaned up now. I mean, the memory occupied by those objects cannot be reclaimed because the references are still alive. We'll come to it. So those objects will be promoted to the generation 1, and from then on, if there are objects which have not been cleaned in generation 1, in the next generation cycle, in the next garbage collection cycle, they are promoted to generation 2, and that is the highest generation. The garbage collector works less frequently in the higher generations and more frequently in the lower generations. So the garbage collector works frequently in generation 0 compared to generation 2. So that is why objects that are created in generation 0 are cleaned up much more frequently, much more often than objects that are residing in generation 2. But again, let me reiterate that these generations 0, 1, 2, these are just logical, you can say logical partitions, you can say logical segments. They are assumed for the purpose of optimizations, performance optimizations by the CLR. So when we collect a generation, we collect all objects in that generation and its younger generations. Due to the fact that a generation 2 garbage collections reclaims objects across all generations, that is the entire managed heap, it is also referred to as full garbage collection. So now when there is a garbage collection happening, and if the garbage collection has happened for say generation 1, in that case you can assume that there has been a cleanup of objects residing in both 0 and 1. If there is a garbage collection cycle that has occurred in or been triggered for generation 2, that means 0, 1, and 2, all the three generations, all the objects residing in the three generations have been attempted by the garbage collector to be cleaned. I mean to say, the garbage collector attempted to clean objects in all the generations. So that is known as a full collection or a full garbage collection, because when the runtime, when the CLR makes a call to generation 2 garbage collection cycle, or a generation 2 garbage collection to be more precise, all the younger generations are also cleaned. I mean to say, when I say cleaned, it is an attempt to clean. So that means in the highest generation, that is generation 2, if there is a garbage collection cycle that has happened, that means that it is a full garbage collection. Now, if you go back to what we were discussing in the earlier slide, the gc.collect, in the gc.collect method, we can pass a parameter, and that is the generation numbers. We can say 0, 1, or 2. If we specify 2, that means a garbage collection will happen for generation 2. If we specify 1, that means the generation 1 garbage collection cycle will be triggered. If we specify 0, which is the default, there would be a garbage collection happening for generation 0. Now, there are situations when you might need to make a call to generation to the gc.collect method, primarily when you see that there are certain objects which are in the higher generation and they have not been cleaned up, and you can see that the application has determined that the system is low on memory. In that case, you can make a call to gc.collect for generation 2, but usually we try to avoid that. Now, from the point of view of the managed heap, the CLR splits the managed heap into two parts. One is the small object heap, or the SOH, and the other one is the large object heap, or the LOH. The garbage collector creates two heap segments. At the time when the CLR is loaded, it creates two segments. One is the SOH, the small object heap, and the other is the LOH, or the large object heap. The SOH implies those objects which are residing in generation 0, 1, or maybe even 2. So, in case of LOH, objects that are having a size more than 85 kilobytes, they are stored in the LOH. So, the LOH, a collection of the LOH happens when there is a generation 2 collection happening. That is the only time when this can happen. But there's a difference between SOH and LOH as far as how the garbage collector works. The garbage collector works obviously much more frequently in SOH compared to LOH, because LOH means you are having much larger objects stored there. The allocation cost is high, and it is, of course, the LOH when it is collected, it would be collected with the rest of the heap, because that is a full garbage collection. So LOH means it is a generation 2 collection. A collection of LOH is a generation 2 collection. Now let us understand the problem with LOH. In the heap memory, when objects are created by the runtime, those objects are compacted by the garbage collector when needed. So compaction is a process that is triggered to improve heap performance. So let us understand what is compaction. So assume that you have 3 objects A, B, and C, and out of those, and all these 3 objects have been stored in the SOH, that is the small object heap, and out of those, the object B has been removed. I mean the memory occupied by the object B has been reclaimed. In that case, there will be a memory hole there between A and C, and this memory has to be compacted, because otherwise that would be a wastage. In that case, what will happen is, when a request for creating another object will come, the runtime will not be able to store this object in that particular memory segment, even if it is free, because it goes on allocating memory space on a sequential basis. So it will not come to that particular block of memory which is free, and over a period of time, this sort of memory holes will add up, and there would be, the system will run short of memory heap. There is where there is a concept called compaction that is triggered, a process called compaction that is triggered, which compacts all these memory holes together into a single place. So what this means is that the compaction process is triggered to compact all these memory holes into a single place. So that means over a period of time, when these memory holes add up and they have, suppose, taken up a lot of memory, the runtime will trigger the garbage collector, which will then compact the memory in the heap so as to allow for more objects to be stored in the heap memory. But this does not happen in LOH. By default, the large object heap is not compacted by the runtime. You can, of course, trigger it by using the code given here, like gc settings.large object heap compaction mode equals to compact once, and then you make a call to gc.collect. In this case, the gc.collect will be making a call to making a full cycle, and that is, it will be making a full garbage collection. So large object heap is a portion of memory where objects that are of larger size than 85 kilobytes are stored. But the problem is that the allocation cost is high, and the LOH is collected much less frequently compared to the SOH. So we should avoid storing objects in the LOH, and that should be the practice that should be followed. We will see as we progress in this session how we can ensure that objects that we create in the application using strings, of course. Suppose we create a collection where we have a number of string objects. What best strategies we can follow to ensure that those collection string objects are not stored into LOH. Okay, so far so good. We will now have a demo on the performance of code snippets that take advantage of strings in C#. We will be using Visual Studio 2022 Preview 7 because we will be leveraging .NET 7, and .NET 7 is not supported in Visual Studio 2022. So assuming we have Visual Studio 2022 Preview 7 installed in our system, we can proceed with creating a new project. It should be a console project in .NET 7, and then we will have to add a library called BenchmarkDOTNET. I'll tell you about that. BenchmarkDOTNET is an open source library for use in .NET applications, using which you can benchmark your snippets of code to understand the performance metrics. For example, if you want to know the amount of time that your code snippet has taken to execute, the amount of memory that your code snippet has consumed while executing, the generation 0 and generation 1 collections, details of those collections that has happened for maybe 1,000 operations or 2,000 operations or 5,000 operations. Then if you are using two methods and you are trying to compare the performance of method X with method Y, where both these methods, the intent of both these methods is the same, so you might be looking for a rank of it, like say which one of these two will be executing faster. So these are all the details that you can capture. There are more that BenchmarkDOTNET has to offer, but we will not be using all of them. So here are the steps that we will be following to get started with BenchmarkDOTNET in .NET 7. So we will create a console application project in Visual Studio 2022 Preview. We will install the BenchmarkDOTNET NuGet package into our project. We will execute the benchmark methods, and then we will compare and analyze performance. Let us now take a look at the project in Visual Studio 2022 Preview that we have created, or we will be building. It is already built actually, to save the time in this demo. So we'll take a look at the project. We'll take a look at the package that has been installed, the BenchmarkDOTNET package that has been installed, and we will be also taking a look at the code snippets, the methods that we will be benchmarking shortly. So here is the project. So the name of the project is String Performance Demo. It was created and some benchmarks were executed, due to which you see this folder called BenchmarkDOTNET artifacts. BenchmarkDOTNET artifacts. This is the StringBuilderCache class of Microsoft, which has been added here because it is not available as part of your usual libraries that you use. And because it is internal, System.text, because it is an internal class, you will not be able to use it unless you copy it in your source code. You will come back to that. And then we have a class called String Performance Benchmarks, where we have a list of benchmark methods. So all these benchmark methods are having this attribute set, and this is benchmark. So this attribute belongs to the BenchmarkDOTNET library that we are using. If you take a look here in the NuGet packages that we have installed, this is the one that we have installed. The other packages will be automatically installed when you are installing benchmark, like benchmark.net annotations and all those stuff. So here is the library that we have installed, benchmark.net, for benchmarking our code. Once you install this into your project, you will be able to use the namespaces of this library, like benchmark.net attributes. So here you have certain attributes that you can use, like say orderer, the rank column, and memory diagonalizer. So this orderer is used to set the order of execution speeds, like from the slowest to the fastest. And so once you have set the orderer, if you have the rank column, you will be able to see which one of them ranks first and which one of them ranks second, as far as the order of execution is concerned, from slowest to fastest. In this case, it can also be the opposite, that it can be also the fastest to slowest, but here we have used this. Now if we are using this order, in that case we should be benchmarking a set of methods which have a common purpose. Like in this case, we have append strings using the string class, and we have append strings using StringBuilder, two methods, but the intent is the same. So we are trying to append the strings. So here this order will work fine, and whatever order it will generate, that will help you to understand the execution speeds, and as far as the ranking of them is concerned in the rank column. So we will see the output that is generated, but we'll now first try to understand this code. We'll go back to the okay. So before we go there, we will take a look at program.cs, and this is how we will execute the benchmarks. So this is the name of the class. So you say benchmark runner.run, and then you say string, and then you pass the name of the class here. So this class contains a list of benchmark methods. So all these benchmark methods, that is, a benchmark method is a method that is having the attribute benchmark on it. So all these benchmark methods will be executed one by one. Now here we have commented out all the other methods except in these two, just to show you how I mean what happens when this is executed. So remember that when you are benchmarking code, you must set your project compilation mode as release. Okay, so if you are to look at the NuGet package that you have installed, I mean the library that you have installed, you can right click on your project and then go to manage NuGet packages. So from the package manager, NuGet package manager, you can see the benchmark.net library that has been installed in this project. You can see the green mark here. Now let's go back to the class that we have Now let us go back to the class that we have created for benchmarking. The name of the class is string performance benchmarks, and it is in a file called StringPerformanceBenchmarks.cs in our project. There are three attributes: orderer, rank column, and memory diagonalizer. Orderer and rank column, these two are used for determining the speed of the methods being benchmarked from the slowest to the fastest in this case. And the memory diagonalizer attribute is used to get information related to the memory consumption of your snippet of code. The memory consumption in GC, in garbage collection cycles like in generation 0 and generation 1. And here is the class that you have two constant variables. One is an integer variable which is having a value of 100. We'll be using this for iteration. And there's another string variable, constant string variable called text, which is having a text variable, a constant string variable. We will be using this for extracting strings, for adding strings, and etc. We come to our first benchmark method, and the name of this method is append strings using the string class. As you can see, we are creating a string object here, assigning it to string.empty. So that is it is an empty string, and then we are using the counter to iterate, and then within the loop, within the for loop, we are adding the text that we have created in the class scope in the previous slide. Now, in the second benchmark method, we are appending strings using the string builder. We are creating an instance of the string builder class, and then we are using a similar loop where we are making a call to StringBuilder.append. So in one case, we are adding the text using plus equal to, so that means it will be adding using strings. Adding the text using strings. So it will go on adding till the value of I reaches the counter, and in this case it will go on adding till the value of I reaches the counter. But in this case, it is string builder append. So that means here we are using the append method of the string builder class. So in one case we are using string class, and in one case we are using the string builder. When you benchmark the performance and you see the results, you will see a massive difference in performance with respect to the string and string builder here, and how the string and string builder performs here. In this case, you can see that as far as the time taken is concerned, in one case the mean is 30.703, and in the other case it is 1.354. So there is a massive difference in performance. Also, when you come to the allocation, you will see in generation 0 it consumes very less memory. In generation 1 also it consumes much less compared to the string object in generation 1. So in generation 0, the collection that is shown here, the number that is shown here is the generation 0 collection for 1000 operations. The number that is shown here for generation 1 is the generation 1 collection for 1000 operations. So you can see the legends here provided beneath the table where the performance data is shown. The mean is, of course, the arithmetic mean of all the measurements. And then when you come to rank, you see that number 2 is the string class, the append string using string class method, and number 1 is the append string using the string builder method. So the rank is 2 for the string 1, and the rank is 1 for the string builder piece. But because we have specified slowest to fastest in our class when specifying the orderer, that is why you see the slowest method comes on top. When you see the allocation, you can see that in one case it is 495.58 KB, and in the other case, that is the string builder, it is just 13.14 KB. So there is a massive difference in the amount of memory. There's a massive difference in the amount of memory consumed, and there's a massive difference as far as the speed of execution is concerned. Okay, we now come to the next set of benchmark methods. This one is create string builder with pool. Here you can see that we are using the default object pool provider to create a string builder from the pool. So here so when I make a call to create string builder pool method of the default object pool provider class, so what happens is that a string builder pool is created. So from then on, that you can use that string builder pool to retrieve a string builder. Like say if you say string builder pool.get, so you will be able to get a string builder instance. So that means a string builder instance will be created right away and it will be returned from the pool. So the pool contains ready to use string builder instances, and once you are done with your work, so suppose you want to append a text and then you want to return it, and you're done, and then you return the string builder instance back to the pool. So that means whenever you are requesting a string builder instance from the pool, if an instance is already available, it will be returned to you. If not, in that case, a new string builder instance will be created and that will be returned. That is how it works. So this is a pool of string builder instances. So here we are appending text again within a loop, and you see the counter variable here again. So that means we are iterating 100 times. So that means we are making a call to StringBuilderPool.get 100 times. We are making a call to StringBuilder.append 100 times, and we are also returning the string builder pool. So that means we are retrieving the object, appending text, and returning the object back to the string builder pool 100 times. In the next example, what we do is we are creating a string builder instance again inside a loop. You see the counter variable here again, but this time we are not using the string builder pool. What we are doing is we are creating an instance of a string builder directly, and then we are appending a text. So in one case, we are creating a string builder using string builder pool, and in the other case we are creating a string builder without using string builder pool. When you see the performance difference, here is what you will see. Like the allocation you can see is very less when you are using string builder with pool, because it reuses the instances. So you can see the allocation when we are not using string builder pool, that is 24,800 bytes, and in the other case it is just 584 bytes. So you can see the difference. There is a massive difference with respect to allocation, because in the first case, when you are not using string builder pool, so the string builder instances are not reused, but in the other case, because you are using string builder pool, the string builder instances will be reused. And of course there's a difference with respect to the execution time as well. When you are using pool, it takes less time. When you are using not using a string builder pool, it takes more time, because in every case it needs to create an instance. And in case of a string builder pool, it can reuse the instances. Okay, we all know that accessing contiguous memory is much faster compared to accessing non-contiguous memory. We will come back to this. The three types of memory that are supported in .NET are stack memory, managed memory, and unmanaged memory. Stack memory is not managed by the runtime, I mean to say the CLR. So there will be no GC there, so no garbage collection cycles. But managed memory is a memory that is managed by the CLR. So you will have garbage collection there. Garbage collection cycles will be there. You also have unmanaged memory, where you can, when you create pointers in your program, or you are trying to access memory outside of the CLR boundary, outside of the CLR's memory space, you are trying to make a call to any COM component. So that is an example of accessing unmanaged memory. Recently, two structs have been added in .NET Core, and these are span T and memory T. So these are generic in nature, and that is why you see T here. So these structs give low-level interfaces to any contiguous managed or unmanaged memory block, regardless of whether the memory is managed, unmanaged, or is on the stack. They represent a type-safe access to contiguous memory block of memory. The primary goal is to encourage micro-optimization and to design low allocation code that lowers managed memory allocations, thereby relieving the garbage collector of any pressure. They also enable you to slice or deal with a piece of array, string, or memory block without having to duplicate the whole chunk of memory. So these are structs. So they provide you low-level interfaces using which you can access any memory, whether it is managed or unmanaged, or is it on the stack, in a type-safe manner. So we'll see more of it. So span T is what we will be using in this session. We'll have an example after this. Span T is an allocation-free value type with almost zero overhead. It provides a type-safe way to work with contiguous block of memory such as strings, arrays, strings, and unmanaged memory buffers. The following are the characteristics of span T. It's a value type. It has zero or low overhead. It is high performant. It provides memory and type safety. This is the span T struct that is defined in the .NET Core library. So you see a pointer there and also a length. Now these are two snippets of code, one that converts an array to a span and another that converts a list to a span. So you can see there is a method called asSpan that you can use to convert an integer array to a span, or a integer list, here in this case, to a span. So the moment you convert this to a span, and from then on whatever you do with it, your collection or your array, so there will be absolutely no allocation happening, because your span, the read-only span or span, whatever instance of it you are creating, span or read-only span, so that they are created in the stack. Okay, we now come to the next set of benchmark tests that we'll perform now. The name of the method is extract string using substring, and the other one is extract string using append. So in one case we are using StringBuilder, in one case we are using string. We also have another version where we are using span. So we have three benchmark methods. In the first one, we are using the substring method of the string class to extract string. In the next one, we are using the append method of the StringBuilder class to extract string. We are passing the text that from which we need to extract the string, and then the starting index and the number of characters to index. The same in case of substring also, we use almost the same parameters. There are two parameters here. One is the starting index, and the other one is the number of characters that you would like to extract. And the last one is another version of extracting strings where we are using span. You can see we are using slice. So we are converting the text to span, and then we are using the slice method. We are passing the starting index and the number of characters we need to extract. When you look at the benchmark results, you will be really amazed to see that when you are using span, there is absolutely no allocation. You see, in generation 0, generation 1, or any, or in the memory allocation column, you see that there is absolutely zero allocation. And of course, using span is the fastest. It takes much less time compared to extracting strings using substring or append. And which it also you can see one thing, like when you are extracting strings using substring, I mean the substring method of the string class, that is faster compared to extracting strings using the string builder. But when you're using substring method of the string class, the allocation is more. There is almost double allocation compared to extracting string using the append method of the string builder class. We use a cache to store data so that we can access it from the cache, when the application can access the data from the cache when it needs to. This is beneficial as far as performance is concerned, because if the data is residing in the database, you don't need to make a call to the database every time the application requires the data. Usually this is used for data that is stale, that will be not be changing over time. So this boosts the application's performance. Caching is a great way to improve an application's performance. That said, StringBuilderCache is a new addition to in the .NET library. I mean to say system.text library. So the StringBuilderCache is a class that you can use to store instances of the string builder. You can cache it for later use. So that means if your application requires the instance multiple times, you don't have to create the instance of the string builder so many times. So in the first example, as you can see here, we are not using StringBuilderCache. So here within the loop, we are creating an instance of the string builder 100 times, and then we are making a call to append. In the second case, that is the second example, you can see that we are making a call to StringBuilderCache.acquire. We are appending text using the string builder instance, and then we are making a call to get string and release. So what happens here is that your string builder, so what happens here is that when we make a call to StringBuilderCache.acquire, if the instance that we are trying to retrieve, that the string builder instance that we are trying to retrieve, if it is available in the cache, it will be returned. If not, a new instance will be created and it will be returned. And from then on, what happens is the application uses that instance. That means here in this loop, you will use this instance to append text, and then when you make a call to get string and release, the string will be returned. The string that has been stored in the string builder instance will be returned, and the string builder instance will be released so that it goes back to the cache again. So that means it is available for reuse. So this is the difference between these two. In one case, we are not using string builder instance, due to which we are creating an instance of string builder every time, and in the other case, we are using it. Here in this case, we are actually using only one instance of the string builder, because in the first call to the acquire method, the string builder instance will not be available. So in that case, it will be created and then returned. But from then on, because the string builder instance is being returned in the get string and release method call, so from then on, what happens is that string builder instance residing in the string builder cache, so that will be reused. So if you benchmark these two methods, you will see that there will be a massive gain in performance. The allocation will be very less, less than 1/3, and the execution speed will also be more than double, or around double. So what happens is that the method that uses StringBuilder, cache, that method will be much faster, less allocation. It will take it will consume much less generation 0 collections. So overall, what happens is the resource consumption is less and execution speed is more. So that is why StringBuilderCache is a great way to boost your application's performance if you want to use or reuse a StringBuilder instance multiple times in your application. Now we come to an interesting concept called string interning. So this involves using a hash table to store a single copy of each string in the string.interned pool. The key is the string hash and the pointer, and the value is the pointer to the real string object. This ensures that there is only one copy of that string allocated in the memory, even if the string appears many number of times. When comparing strings, you only need to perform a reference comparison if they are interned. So let me give you an example. So suppose there is a string called hello world, which has been used 100 times in your code, in your program. So only one copy of that string will be stored in the memory, and from then on it would be referred that many number of times, like 100 times. But you will not have 100 copies of the string stored in memory. There will be only just one copy. So this saves on the memory. This saves on the memory that is consumed by your application to store a string literal or a string constant many number of times. The intern method in C# is used to obtain a reference to a specified string object. This method looks into the interned pool for a string that is identical to the supplied string. If such a string exists, its intern pool reference is returned. But although string interning is an exciting feature, it should be only used sparingly in practice. Misusing it can undoubtedly adversely affect your application's performance. We should only consider it if we plan to create many strings with the same content. Let us now take a look at the characteristics of the string interning. The memory location of two identical interned strings will be the same. So that means if we are having a string literal, say hello world, and again you are creating another copy of the same literal hello world in your application. So the memory location of both the strings will be the same because they are created in the memory only once. Until your application is terminated, internal string memory is not released. So mind it, if you are using string interning, you should ensure that you are not misusing it, because when you are using string interning, these interned strings, these string literals or these string constants will not be released from the memory until the application is terminated. It does not get released automatically when the control comes out of the method. In order to intern a string, a hash must be computed and the string must be searched in a dictionary, which both consume CPU cycles, CPU resources. Since the dictionary of intern strings is serialized, several threads interning strings simultaneously will block each other. Interning a string requires computing a hash and searching a dictionary, both of which consumes CPU cycles. When you use the same string several times in your application, it will only keep one copy of the string in memory. This will reduce the amount of memory you need for your application. If you have a lot of intern strings, string interning can be slow as threads will block each other as they access the intern string dictionary. So these are some of the points that you should keep in mind when you are using string interning, because string interning, though it might be handy, though it might yield benefits as far as memory consumption is concerned, but if you use it too many times, if you are creating too many intern strings, string literals or string constants in your application, they will be consuming resources till the time the application is terminated, which would become a bottleneck as far as performance is concerned. Now we come to a code example which will illustrate string interning. So you will now be able to know how exactly it works. When you try to intern strings using a string builder and then making a call to the string.interned method. So you see the string object S1. So we have assigned demonstrating string interning, this literal, this string constant to S1. S2, when we are creating S2, we are creating a instance of string builder. We are appending demonstrating, and then we are appending string interning, these two strings, and then we are making a call to toString to convert that string builder instance to a string. And then lastly, what we are doing is we are making a call to string.intern, and then we are passing S2. So that means S3 is interned along with S1. S1 is also interned because that is a constant. That is the string constant that you have assigned. So now when you run this program, run this piece of code where you are checking whether S1, S2, S3, I mean they are the same. You will see that S1 and S2 are two different references, but S3 and S1 are the same references. The reason is because when you are creating S2, you are making a call to string builder, you are making a call to the append method of the string builder, you are making a call to toString to convert that to a string. So that is altogether new string instance being created. But when you are making a call to string.intern and passing S2 in order to create the reference S3, that is a same reference. That is the same reference as S1, because that will be pointing to the same memory location. When you compare strings using interning, here is what happens. Like say you make a call to string.intern, you pass the string, and then you use the intern string. You check whether the string str and s2 that has been created are both the same, and then there is another compare method where we are not using interning. We are comparing str and s2 again, but in this case we are not using string interning. So this is just making a string compare. So in this case it will be taking a lot more resources and time. Let us see the results. So when you benchmark the performance of these two methods, you will see there is a massive difference in performance. And rightly so. There is no allocation when you are doing a string interning, because string interning, the string is not created in your small object heap. It is created in the large object heap. So you will not see any allocation here when you are using string interning. So you also see there is a massive difference with respect to the execution speed. So in one case it takes 1475.11 nanoseconds, and in one case it takes 93.20 nanoseconds. There's a massive difference in performance. And there is no allocation on generation 0. There is no allocation absolutely of memory in the heap. And here the heap actually refers to the small object heap, not the large object heap. So because the because the intern strings are created in large object heap, you will not see any allocation reflected here. This example stores intern strings in a list. So you can see that we have created a list of strings. We are interning strings, and then we are storing it, and then we are adding to the list. So here temp. So we are checking if temp is null, we are interning it. Otherwise, we are adding it to the list. So the first time it will check if temp is null, and because temp is null, it will intern it, and then the next time it will add it to the list. But so that means from then on there will be no calls to string.intern. In this case, in the other case where we are storing strings in the list, but these strings are non-intern strings, here we are making a call to list.add directly. So here we are not using intern strings, so this will be much more resource intensive. So let's see the difference. When you benchmark these two methods, you will see that storing intern strings in a list is much faster compared to the other option, that is storing non-intern strings. The allocation is much less, more than 1/3 reduction in the allocation. The generation 0 collection, generation 1 collections will be less. It will be much faster with respect to the execution speed as well. So this is what. So string interning, again, before we conclude on this part, so string interning is a great option to boost your application's performance, provided you're not using too many intern strings and you are using string interning judiciously. You should not use string interning when you have little strings, but you are not using too many times. So there's no point in doing that, because when you are doing that, it is unnecessarily consuming space, consuming memory in the large object heap, and not only so, it requires memories, CPU cycles as well. Okay, so before we conclude this presentation, let us take a look at how strings are represented in memory and the best practices. While strings in C++ are represented in the form of PWSZ, that is pointer to wide character string zero terminated rule, in C#, strings are stored in the memory based on BSTR, that is basic string or binary string rule. In both cases, the strings are terminated by null character at the end. In the BSTR rule, each character in the string consumes 2 bytes and is in the UTF-16 coding, that is 2 byte characters of the string in UTF-16 format. A string instance comprises of the following: an 8-byte object header, which comprises of 4-byte sync block and a 4-byte type descriptor. The length of the string represented as a int32 field. So this has been deprecated after .NET 4. We don't need it anymore. A total count of the number of characters in the character buffer represented by an integer 32 field. The first character of the string represented as system.char. A character buffer that contains the remaining characters of the string, terminated by a null character at the end. So the length of a string on x86 system is 14 plus length into 2 bytes, and on a x64 system it is 26 plus length into 2 bytes. So that means if your strings are empty on a x86 system, it will consume 14 bytes, and on a x64 system it will consume 26 bytes. Now we come to the best practices that can be followed for making best use of strings in .NET. So whereas the .NET, it applies both to .NET Framework and .NET Core, and of course the latest version of .NET, that is .NET 7. Use StringBuilder for appending strings multiple times. Use span for allocation-free access to contiguous memory. Use StringBuilderPool to reduce allocations so that you don't need to create the StringBuilder instances multiple times. The same applies for StringBuilderCache as well. So you create a StringBuilder instance, store it in the cache, and then you go on using it. Use string interning to reduce allocation if you are having a string literal or a string constant you are creating multiple times. The same string constant, the content is the same, you are creating multiple times. To extract a string from another string, always use span t here. Span t here, it implies that it is a generic type, so you can use it with any type. So if you are using span for extracting a string, that is a substring, you are trying to do a substring, it will be very fast and there will be zero allocation. Here are some suggested readings. And thank you for spending the time to view this presentation. The best way to contact me is through my email or my website. I have provided the LinkedIn, Twitter details as well. I blog at InfoWorld. and I have also provided my GitHub URL where I frequently upload code snippets. Thank you.
Thanks, Joydip. I'll remind you that we're very interested in your feedback about this webinar and would appreciate you taking a moment or two to complete our survey. It's all of 12 questions, so you'll fly right through it, and one lucky attendee will receive a $100 Amazon e-card. Just a reminder that as a benefit for registering for this webinar, all registered attendees who don't already subscribe will automatically receive a free digital code magazine subscription. Upgrade your subscription to a print subscription and receive our .NET 7 Code Focus issue free while supplies last. Please share the subscription link here with others who couldn't make it to the webinar. Code Consulting is hiring. Come join the Code team. We have multiple positions currently open, remote and on-site. Full-time and contractor positions are available. Follow the link for more details. Through our free hour of code, you can ask for our help on whatever your team needs. No strings, no commitment, no credit card required, just help from our code experts. Reach out to me about getting your free hour of code scheduled. The Code mobile app is available for both iOS and Android. It's the ideal way to read Code Magazine on the go. Register today for our Secure Coding for C# Developers course and learn to develop robust and secure C# applications in our online 3-day hands-on course. Register today for courses starting in 2023. Okay, that's it for today's presentation. Don't forget to subscribe to our YouTube channel, like us on Facebook, and follow us on Twitter. If you're attending live, we'll be in the chat room for a while answering as many questions as possible. If you're watching the post-event recording, please don't hesitate to reach out to me or through any of our communication channels. Thanks for attending, everyone. Have a great rest of the day or night wherever you are.